Hey guys, so today we're in 5.7, which is graphing absolute value functions. So we're going to learn how to graph the parent function of an absolute value, and then we're also going to learn some of its transformations, okay? So in absolute value of x, we know that the absolute value, being a distance, means that distance is never negative. So if we put a -3 inside an absolute value set, that it will give us back a +3. Likewise, we can fill in this table in about 1 second, okay? Now we're going to learn what that graph looks like, okay? So x, y, 3. There we go. Okay, so we're going to learn what the graph looks like. Now, the parent function is always the function that we use to understand any other types of transformations, okay? So if x is -3, y is 3. If x is -2, y is 2. Likewise, we will plot all of the points from that table. So what we see here is that when we connect these dots, that we get a perfect V. So in other words, each branch of the graph, the left and the right, go through where each grid on our graph paper intersects, okay, or where it meets. So that is what the absolute value function looks like when we graph it, okay? And then there are transformations that we can perform to that by moving it up, down, left, right, etc. Okay? So in example 2, we're graphing y equals the absolute value of x plus 4. So here is where we're going to understand the transformations in terms of x and y, and then h and k. All right, so if we have an absolute value equation that looks like that, okay, there is no movement to the left or the right. This plus k represents that we are either moving up or down, okay? Likewise, if we had an absolute value of x minus h, the h value tells us whether we are moving left or right, okay? So h is left or right, k is up or down. Then, of course, we will have the whole thing thrown at us at one time where we'll move left or right and up or down, okay? So we've got these 3 main equations right here. The one that we're graphing has a +4 outside the absolute value symbols. That means that we are moving up 4. So the parent function, remember, very, very, very easy to graph. You've got your vertex at the middle, and you've got a perfect V. Okay? Now what we're doing is we're going to be moving the vertex up 4 and then regraphing the whole entire graph. Okay? So 1, 2, 3, 4. And from that point, our graph will come out as a perfect V. Okay? Very, very easy. Another transformation, okay? Y equals the absolute value of x minus 4, which means that we're going to take the parent vertex at 0, 0 and move it down 4. And from there, our graph branches out to a perfect V. Okay? Easy enough. So what we can do then with that skill is look at a graph to determine what the equation is. So if we had a graph that looked like this, okay? And we were told to write the function rule for that graph, knowing that the parent function looks like this and has its vertex at 0, 0, our transformed graph has moved up 1. So the absolute value of x, which is the parent, moved up 1. Okay? Easy enough. And the domain of these absolute value functions is all real numbers. Okay, now what we're doing is looking at this transformation of the absolute value. Okay, one thing that we need to understand is that the standard form of this is always y equals x minus. Okay, so if we end up with, say, an absolute value of x plus 3, that only means that it was originally an x minus a negative 3. Okay, so that's going to help us understand whether we're moving right or left. Okay, because this is a right or left transformation. When we've got a value inside with the x, that means that it is a right or left transformation. Okay, so we're on example 4, and this is exactly what we've got, is y is equal to the absolute value of x plus 3. Okay, a plus inside means that the 3 was originally negative, so negative moves to the left, while positive moves to the right. Okay, so that means that we're taking our parent function, the absolute value of x, which is this one right here, okay, and moving the vertex 3 units to the left. So 1, 2, 3, and then I will construct my perfect V from there. Okay, so let's look at another one. Y is equal to the absolute value of x minus 2. Remember that the format is x minus some h value. Well, because we have a minus, that means our h value is a positive, and positive moves right. Okay, so it would probably make more sense if I just said whatever you're looking at as a value inside the absolute value symbols with the x. If it's a negative, go the opposite. So normally you'd think negative was left. If you see a negative, move the opposite of that and go right. If you see a positive, move the opposite of that and go left. And that's when you're inside the absolute value brackets. Okay, so we're taking the parent function, moving it 2 to the right, and replotting our graph. Very, very simple. Okay, now we're going to do everything at one time. X minus h plus k. Now, of course, the plus is not always a plus. It could be a minus, which means that we're moving down, okay? But again, this is just standard form. So if we were to graph something that looked like, say, y is equal to the absolute value of x plus 2 minus 3. We need to decide one transformation at a time where the parent graph is moving, okay? Let's start here because that's always the easiest place. A minus 3 means that the graph, the parent function, is moving down 3 units from its original starting point. Okay, now let's look at what's inside the absolute value. We know that it's moving either to the right or the left. Remember, if you see a plus sign, think of plus as moving to the right and go opposite that. So we're moving 2 to the left and down 3. So we're taking our original starting point, moving 2 to the left and down 3. And this now is where we would be starting our graph. Okay. And there you go. Okay. One more. Let's graph y is equal to the absolute value of x plus 1 plus 4. Okay. So obviously from our k value, we're moving up 4 from the original starting position of the origin and left 1. Okay. So the origin is our original vertex. We'll move left 1, up 4, and replot our graph. Very, very simple. Okay.